All right, the video today is on mathematical models, a catalog of essential functions. The short version behind this video is there are a number of different types of functions that you've worked with before in your life. Today is intended just to be a very quick review of the many different types of functions, their names, and here is a ton of vocabulary based on them. So the quick read: mathematical model, linear function, empirical model, linear regression, polynomial, coefficient, degree, quadratic, cubic, power, root, reciprocal, rational, algebraic, trigonometric, exponential, logarithmic functions. You should have encountered all of these before. Are there any of them that right away seem like they're foreign? That way I make certain I emphasize them a little bit more. Empirical model, okay. All right, so starting off then. Here's our first example. As air moves upward, because you know, especially heat rises, air will expand and cool as it goes higher and higher and higher up. If the surface temperature or the ground temperature is 30 degrees Celsius and the temperature 1 kilometer up is 10 degrees Celsius, express the temperature as a function of height, assuming a linear model is appropriate. Basically, create the line that goes through the points. So, draw the graph. Well, we would start off by saying we're creating the temperature as a function of height, which means the height is the independent variable and temperature is the dependent variable. Well, what are the 2 points that we have? At a height of 0, the temperature is 30. So we have 1 point. And at a height of 1, it's at 10. So we would have those 2 points, which we could continue farther thusly. So we'd have 2, 3, and as many as we needed going to the right. There's a quick sketch for part B. Part A, though, said create the linear model. Well, if we want to create a line, we have slope-intercept form. We also have point-slope form. Which one would be better in this situation? Well, do we actually have... We're going to have to get the slope either way, but do we have the y-intercept? Yeah. Thank you, Scotty. Y-intercept's 30, so we can simply say that's 30. What is the slope, though? We know it's our delta y over delta x. More commonly said, just rise over run. So to go from there, what's the rise? Down 20. And the run is 1, so our slope is negative 20, which will allow us to create the formula using the correct variables. Temperature is negative 20 times the height plus 30. We'll use that model for part C. What is the temperature at a height of 2.5 kilometers? We'll just plug it in. So temperature is negative 20 multiplied by negative 2.5. I don't know why I wrote a negative. We're going up 2.5, not down, so let me correct that. It's the positive height plus 30. So what is 20 multiplied by 2.5? Okay, so negative 50 plus 30 would yield a negative 20 degree Celsius temperature at the height of 2.5 kilometers. which would be really, really cold. Putting it into perspective, you guys know how high 2.5 kilometers is? 1.6 kilometers is a mile. So this is an elevation of about 1.5 miles. There are lots of places in the world that have that elevation. This is just saying, assuming a linear model is appropriate. What if a linear model is not appropriate? We'll actually address that coming up in a future problem. So, I had this part set up there so that we could sketch the graph. But this wasn't appropriate, so that's why I skipped it. Okay. You mentioned that you weren't sure about an empirical, in the vocabulary, empirical model. Empirical just means based on evidence. You remember all the stuff where you did linear regression with the calculators? Those were empirical models. The equation was not a perfect 100% fit when you did linear regression. It was based on using statistics and the evidence that was available. You were not told this is a law. You had to figure something out that said this is best guess. That's what we are doing here. We need to create a model based on this data. In order to do that, I have the TI-84s for you so that you could enter the data and create the linear model. So, quick check, do you remember how to do them? Grab the calculator, type in the number, and go. While you are entering the data, I'm going to plot the points. So we would have 1, 1, 2, 2, 3, 1.3, 4, 3.75. Oh, that's not right. Yes. Yes, Darian, it is located under Stat, Edit. You'll have to type them into List 1 and List 2. And then lastly, 5, 2.25. You're familiar with how to do these, Brian? Okay, coming over under the Stat menu, you'll type in Edit, and then you'll type the information into both List 1 and List 2, keeping the same order that's already there. To clear it, you'll go up, highlight List 1 or List 2, press Clear, and then Enter. 3, 4, 5, and List 2, 1, 2, 1.3, 3.75, and something up on mine. 1.3, 2.75, 2.25. Okay, once they're entered, you can go into Stat, Calc, scroll down to LinReg for linear regression. Press enter again, and it will give you the linear regression model. Assuming we all typed them in the same, we should have gotten y equals ax plus b on the calculator is listed 0.425x plus 0.75 for the linear regression model. That's an indicator that using a slope of 0.425 and a y-intercept of 0.785, which would be something about like this, that line is the best possible predictor of any line. Please do the same thing, or I'm getting ahead of myself. Now that we have this model, his weight change is based on this. If he were to eat 0 candy bars, predict his weight gain. Yeah, if x is equal to 0, This part just drops out. Okay. Now you'll note I have not yet been using function notation. I've been using like the algebra 1 y equals stuff. We could just as easily be saying the weight gain with an input of 0 is 0.785, where we are using the y as the function name as well. Okay. You have your calculators. Please do the same thing. If he eats 8 candy bars, predict his weight gain. So we're taking, of course, 0.425 multiplied by 8, and then adding 0.785, which would yield the total. I'm sorry, I did not hear you. 4.185. So a little bit over 4 pounds, which would have been a pretty awesome estimate if you were guessing. Here's one of the big things. In science, there is the understanding that almost everything is coming from something that is measurable. And therefore, since you can't measure accurately to infinitely many decimals, you have to round. And because you know you're working with rounded values, you have to use significant figures. But in mathematics, most of the time, we will actually assume we are working with perfect numbers. That when we say he ate 8 candy bars, he actually did eat 8 whole candy bars and no crumbs fell off. When we say he gained 1 pound, the assumption is it's a perfect 1 pound. In reality, we know that could almost never happen to have perfect measurements like this. But mathematically, we'll work with it while we're learning the pieces. And then as you go further with math, and now that you have all these other things that are weird, start working with things when they're thrown off a little bit. There are whole other areas of math that would delve into that further. Whole other conversation. So quick checking. Do you remember what these are? Do you remember what they look like anyhow? Could you just give me an example? Polynomials have to have the form like x to the n, x to the n minus 1, x to the n minus 2, blah, 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 until you get down to just like a constant. So the short version is your exponents all have to be positive numbers. No fractions, no decimals, no negatives. They have to be whole numbers. And of course, you would also have all your different coefficients, which could be anything else. And I should have given myself a little bit more room. Okay, the degree is the biggest exponent, the largest exponent on your polynomial. Yep, no matter, well, the power is. It doesn't matter what order they're in. So, for example, if we had x to the 5th plus x to the 7th plus 32x, the degree is 7 because the largest exponent was 7. It has nothing to do with the 32, which is the largest coefficient. You should remember, short version informally. They're the constants that are being multiplied by the variables. Usually we write those numbers in front. So polynomials frequently could be like 2x cubed plus 3x squared minus 2x plus 4. This is written in descending order. I'm sure you remember. What are quadratics? What are quadratics? People are giving me the peace sign, saying it's 2. And a cubic. Some characteristics to remember about these. If you have a polynomial, They're smooth. There are no jumps. There are no gaps. They look, well, that part I messed up on because that would not even be a function. But something like this could be an example of a polynomial. We know quadratics always have what shape? There's our parent function. Cubics, you guys have drawn it out for me, but they have this general shape. And we know with a cubic, it's possible that it could actually come down like that, or have reflections, or a number of other different transformations, but this is the base. So, once again, we are going to use our calculators. While you are typing in the data, I will create the scatter plot. You'll also note I have not been labeling the axes. It's just in an effort to save time. We know that this should be listed as number of AIDS cases in thousands on the vertical axis. The year listed on the horizontal. I should have a title. I've been leaving them off just to shorten the video up and save time. So 99, there were about 40,000. And in 2000, 2001, a little bit below 40,000. And 2002, we got up to 41 and a little bit over. And then 43. So about there. So what do you think? Linear model for that? Yeah. If we're trying to do a line, that's a pretty good line for most of them, except 2003. And so if we're trying to start filling it in, that looks like it could be pretty good. For all we know, maybe off the end, it was like that. Do we really know? So two possible guesses that we could have. It would be possible that with the filled in guess, maybe this is a quadratic model. Maybe without the other pieces filled in, this format would be an exponential model. Well, your guess is as good as mine. Do you think we should guess quadratic regression or guess exponential regression? What are the features available on the calculator? Okay, so let's do a quadratic regression and see what we get. Please type in the information and tell me the numbers. Have you completed the regression yet? Okay, tell me what the AXP would. So we'd have our AIDS function based on the years, that's our first coefficient. Because I'm running out of room, let's go 2 decimal places for it. So 0.14. Okay, I was missing that part. So 345.14 y squared. 9.5 times y, and then the third, 138,126, 247,3. Okay. So those are some glorious numbers. You know what you do to actually fix this stuff, to make it less god-awful weird? Instead of saying 1,999, why not just start with 99, 100, 101? And then you would just say the note, this is starting off years from 1900. Or if you really wanted to, you could say 0 is 2000, -1 is 1999. And so you could adjust the scale on it so it's not so crazy weird. Yep. So use this model to predict when is this going to hit 100,000 AIDS cases. So we're saying, when is it that we get 100,000 equal to 345.14 y squared minus 13808,965 y plus 138,126,2473. When is that true? Okay, remember, I don't want to go through and do the algebra on this. Yes, we could use the quadratic formula. The calculator would probably be the quickest technique. If you don't mind, type this into equation 1, type that into equation 2, and then you can use the calculator's intersect feature to figure it out. You look a bit perplexed, Rebecca. Do you remember how to do that? Okay, so y1 is 100,000. y2, we'll type them in, 345.14 x squared minus 1380896.5 plus 138,126,2473. Okay, I'm going to change the window to be a whole lot bigger. My window I'm going to set from 1950 to the year 2200 for my x minimum and my x maximum. I'm using 1950 and 2200. From there, I'm going to click zoom and go down to fit, because zoom fit will give me the correct y values that match the x window I picked. I used 1950 for the x minimum and 2200 for the y. Do you see the two intersecting when you did zoom fit? 1950. Okay. I'm not getting the same graph that you guys are. So, window. Okay, I see why. When we did them, the y minimum on my window is 100,000, which tells me the bottom of the screen is there. Yep. I want to check my equation to make sure I actually typed it in correctly, because my graph just, it looks wrong to me. 138,0896.5. Ah, I see what I did. When I typed mine in, I forgot to put in the times x variable, and so this middle term was entered as a constant, which allows me to do that and fixes it. But I'm going to have to go and do the zoom fit again. Okay, and you see how when you're looking at it, it's bottoming out pretty close to there. If you go into second Calc, it's the trace button, they have the intersect feature. And it will go through and show you first curve, hit enter for second curve, hit enter for the guess. It'll run through and give you all this information. And mine came out to be 2014.79. So based on the data from 2003, if this is a quadratic model, they're predicting that right about now, because 0.8 is 80% through the year, 80% of 12 months is about 9 months, so pretty much at the end of September, based on this model from 2003, there should be 100,000 people living with AIDS in the United States. Please note, that is not HIV, that is actual AIDS.
So that's like say next week.
If this,
If it was accurate.
no.
Or is it?
We could have that conversation when the microphone's not going because I don't want to waste too much time. Okay, so run through the work there. Let's go with these other ones. What is a power function? Yeah, basically, you have an exponent. So something like x to the fourth power. You could also have a coefficient, so you could have something like negative 3x to the fourth power. That's a power function. What is a root function? So if we're writing them out, that would be something like the cubed root, 1/3 power. The reciprocal function. The reciprocal function is the very specific one. 1 over x, or x to the negative 1. In general, power functions, you should remember, would look like that. Root functions typically would look, and the reciprocal function has that structure. They are all looking familiar? Okay. I would like to point out the textbook does provide a little bit more detail. This is intended to be just a quick, hey, is it completely foreign to you instead of anything else? Do you remember what an algebraic function is? Basically, I'm seeing a little bit more trepidation in the answers on this one. If you can use addition, subtraction, multiplication, division, or roots, you will create an algebraic function. So something like x, we have a power. We have subtraction. We have a square root with addition. That's an example of an algebraic function. No, we do not have to have all of them. All of these other ones that we were already doing, the power functions, root functions, reciprocal, those are all also algebraic functions. I'm also realizing right now, I forgot to put on the video a rational function. Rational functions are a ratio of two functions, but both of these must be polynomials. For example, x squared minus 1, 2x cubed plus 1. That's an example of a rational function. It is also an algebraic function. What about trigonometric functions? What do they have to have? Sine, cosine, tangent, and what are the other three? Okay, they started off giving me cosecant, secant, and cotangent. So quite simply, one of them could be cosecant of 2 theta. That's one possible function. Of course, there are many others. So, quick review of some of the trig ones. What is the domain and range for sine, cosine, tangent? What are the possible domain values for sine, which I'm doing? I'm going to make my colors match the color on the picture. So sine is done in yellow, so what is the domain of the sine? Thank you, Anna. All reals. The range? No. Can you get something that gives you a sine that equals 4? This is capped off a maximum height and a minimum height. They never go outside those bounds. So we do not get all reals. -1 to +1 for range of sine. What about cosine? Same thing. What about tangent? What is the domain of the tangent on this right-hand side? It's done in blue. Okay. But we don't have all reals, though. Yeah, we do have asymptotes here. Do you remember where the asymptotes come from? Zeros of, specifically, tangent, you should remember, is sine over cosine. So anywhere that cosine is equal to 0 is going to present a problem. Well, remember, 0, the cosine of 0 is 0. The cosine of pi is 0. Coming back around, so we had, where was I? Cosine. Okay, cosine of pi over 2. Cosine of 3 pi over 2. I was thinking of sine. I don't know why I said sine. When I had the picture in my mind, I was thinking sine, but I said cosine, and I don't know why I misspoke. I apologize for that. But pretty much, you've got 90 degrees, shift another 180, up to 270. Shift over to -90. Shift over to -270, and another. They're just the 180 degree coterminals. So we could say the domain is all the reals except any x value that is a multiple of pi over 2, with k being in the integers. I told you guys we'd get back to set no builder notation. So pretty much, this is just a way of writing out 90, 270, so on and so forth. They'll be the integers. If you'd prefer, accept anything that is -270, -90, +90, 270, continue the pattern, and you could use degrees that way. Except I can't get my set builder notation drawn. Bad set builder. Start by doing like a little backward S, and then a regular S. Or a regular S, and a backward S. So exponential functions we already looked at. That would be something like 5 to the x, where we have a constant raised to a variable. And we know their basic format. We know logarithmic functions could have a different base, but their basic look branches off and flattens out. So, what type? Okay, this one's an exponential function, true. What of the others? Okay, u of t. I don't know what you're saying. Oh, so you skipped D. Oh, okay, I understand. You skipped C, we'll come back to it, and went to D.
No, we skipped C and went to C. We said C was a trait function.
Okay. Okay, so we have a trigonometric function. It is an algebraic. It's one type of algebraic, that is true, but there is a more specialized name for it. Yep, this is a cubic. Of course, it's a cubic, it's a polynomial, you could say it's a rational function because it's over 1 for a polynomial. It's an algebraic function. There are many different types. Okay. And what else? Okay. You said rational. Why is this not actually rational? Exactly it. Rationals must be polynomials. That one is not a polynomial in our denominator. We'll have to leave that one as an algebraic function. Yes, p of x has two polynomials for the numerator and denominator, so we have a rational function. So, again, this is intended to be just a really quick, remember all those functions you did? You don't get to forget them all. Because, of course, with calculus, when we're doing examples, we're going to take and build upon your skills. We will start working with derivatives and integrals of all different types of functions. And of course, with more complexity in the function, that will frequently cause more complexity in the calculus as well. That's why we will start off with very simple things like doing limits of a polynomial, doing limits of some piecewise functions, doing derivatives of polynomials, and more simple functions. But once our skills build, we can progress further into more complex functions as well. Any questions over our topic? Okay, that completes our work. Have a good day. Okay.